exponential processes can be a little tricky to solve. They're not your typical equation. And what makes them interesting is, imagine, for example, you're in a rocket, like this one here. Imagine you're in a rocket, and soon after they light the candle and you're blasting off the launch pad, you estimate that the force you're feeling pushing you back into your seat is a certain amount, like, 1.5 Gs. Now that's going to be a constant force generated by the rocket engines pushing you up in the air. But you'll find that your acceleration increases as you get higher in the air because the fuel inside the rocket is consumed. That makes the rocket lighter. It will weigh less. And when you have the same amount of force pushing something that's lighter, the acceleration will be higher. And you'll get pushed further and further back into your seat, and it will feel to you like the force is increasing. And rockets often experience a period of maximum stress, which is not initially at launch. It's further up once some of their fuel is burned off and the rockets are lighter, but they're still blasting away. So it makes the equations of motion a little tricky. And you'll see here, this equation of motion is not what you're used to looking at. It has exponentials in it. And we're going to work through how to solve something of this nature. So you'll notice one thing is very, very easy. Delta V is asked for, and there it is. That's the thing I want to solve. I want to figure that out. You'll notice something else is given to us, and that's also straight up very easy. This right here, the exhaust velocity, that little guy, is 3.75 kilometers per second. That's how fast things are getting shot out the back of the rocket. Okay, well, that's great. But MF and M0 are not quite so clear. You have to do some reading to find those. So let me just walk you through how to do that. Let's focus on what MF is. This is the dry mass of the rocket. Okay, and that is the mass of the empty rocket shell plus whatever is carrying up into space. Now, the empty rocket shell I see here is 89 tons. And the mass of whatever it's delivering up into space is 120 tons. So that means, in this example, MF is 209, right? MF, the final mass of the rocket, is going to be the initial weight of just the empty rocket plus the mass of the payload. Okay, so that's 209. And then M naught is something different. M initial, this is the initial mass of the rocket. And what that means is it's just the final mass of the rocket plus all the propellant. This is before the propellant has been shot out the back. So M naught equals 209 plus this right here, 1,200 tons of propellant. So that's going to be 1,409. So the initial mass is 1,409. The final mass is 209. And now we need to solve for delta V. Well, let me rewrite the equation, having put in a bunch of numbers. Okay, so we're going to have M naught, the initial mass, that's 1,409, equals M final, right? This is the mass when it gets to its destination, no fuel left, times E to the, to the delta V divided by 3.75. So you'll notice this is an exponential equation, and the way to solve exponential equations is to first get the exponential by itself and then use a logarithm. So what I'm going to do here is divide each side by 209. Okay, let's see what we get. 1,409 divided by 209. That's 6.7416. I'm going to use lots of decimals. 6.7416 equals e to the delta v, that's the thing we want, divided by 3.75. Okay, so now all we have to do is take a logarithm of both sides. And what we're going to do here, let me just set up this idea of a logarithm of both sides. So there's delta v over 3.75, like that, that's a 3. And the question is, what should I have the base be? What should I choose for my base? I could pick anything. I could pick 10, 30, but there is one number that's very useful, which is e. And the reason I want to pick e is because that matches the base on this side, things are going to cancel out very nicely. Now, I'm not actually going to call it log base e, right? We have a special word for that. This is the natural log. So the natural log of 6.7416 equals the natural log of this thing. Well, let's just work through some math. Now the natural log on the right, something kind of cool happens here, which is the power rule. The exponent drops down in front, and what you have left is ln of e with no exponent. Now that cancels out. That's just equal to 1. So we get this. The natural log of 6.7416 equals delta v over 3.75. Multiply each side by 3.75, and there we have our answer. 3.75 times the ln of 6.7416 equals delta v. So let me just plug that into the calculator. See what we get here. 3.75 ln of this thing. There we go. 7.156 kilometers per second is our delta v. In other words, if we're saying how much velocity change will this rocket have, well, that's 7.156 in this case, which is an appropriate amount considering what's being asked for in this problem. Flying from Earth orbit to Mars orbit, it's going to take some fuel.